This video will give a brief outline of all the work that was done by the Lygus Vacuum Imaging System team. The Lygus Vacuum Imaging System team worked alongside the other Lygus vacuum teams with the goal in mind of successfully imaging and counting all Lygus found inside the vacuum. With little to no high-speed imaging experience, the Lygus Vacuum Imaging System team went into the project with the mindset that it was going to be heavily research and development based, with multiple tests and multiple trials to find the right system. Our initial testing design consisted of a PVC pipe with a leaf blower attached to it and a camera that we had rented from the library attached to a tripod. We would drop imitation Lygus, which were at the time beads, into a hole cut out right in the mouth of the leaf blower, and we would attempt to image these beads using the camera seen on the tripod here. In this test, you can see we were just using ambient light and a couple LEDs that we had bought from the store. In this video here, you can see the leaf blower is barely at an idle, causing the beads not to fly very fast. One of the problems we ran into early on was trying to get a consistent speed of the beads to match what they would actually be inside the vacuum. You'll now hear the throttling up of the leaf blower in which we attempted to get higher speed bead images. Here you'll see a slow-mo video from one of our initial tests, as well as a still shot in which you can see the streak from an imitation Lygus.
Okay.
Sweet.
Well, so where's the bug?
Yeah, so you can kind of see it.
Our initial results proved to be somewhat promising, as we were able to see a very, very vague streak of what appeared to be an imitation Lygus bead.
And we're not even, that's probably around like 30 miles an hour too.
Yeah.
3 improvements that were made to the system consisted of an electric leaf blower in order to provide consistent wind speeds, a strobe light to control the visual light exposure on our system, and a DSLR camera in order to take higher resolution videos.
After realizing it probably wasn't the best idea to be running a gas-powered leaf blower for hours on end indoors, we moved to a higher-powered, more consistent electric leaf blower. Another thing you can see in this video is the use of a strobe light. We realized from earlier tests the streak was being caused by the ambient light as well as the LEDs, so we knew we had to find a light that had a flicker speed that was faster than the shutter speed of the camera. Using the strobing method and this setup, we were able to successfully and clearly image imitation Lygus within the system. Over the next few weeks, we ran many tests using different amounts of imitation Lygus, different colors, as well as debris in order to try to find desired results. After every test, we would upload our images to the computer, in which Jack would run them through his MATLAB code. The goal with this was to see how many actual Lygus we successfully imaged out of how many were actually dropped into the test system.
Here's a close-up video of one of our tests where you can see media being fed in just downwind of the electric leaf blower. Notice how the imitation Lygus flying around 50 miles an hour is only seen when illuminated by the strobe light. This is an instant in time taken from one of our tests where you can clearly see imitation Lygus in the PVC pipe. Notice there is a thin black line at the top of the PVC pipe. Frame blending, which is an internal process for DSLR cameras, was disrupted by the strobing effect. Because of this, an instant in time was stretched over multiple frames and had to be later stitched together in MATLAB in order to analyze an image. This is a post-process version of that same image after it has gone through multiple filters dealing with the size, shape, and color of our imitation Lygus. The MATLAB code goes a step further and counts how many objects it believes is an imitation Lygus within the frame. That number is then totaled across all frames in the video. The MATLAB code disks miscount from time to time. For instance, in this image you can see that the Lygus boxed in red were not counted by the code. This could be due to the Lygus media being on the line where the frames were blended together, the orientation of the Lygus, a boundary overlap problem, or simply the Lygus media being caught in the shadows. After analyzing multiple tests, we noticed that only about 8% of the Lygus media that was thrown through the tube was actually captured on footage. This was mostly due to the strobe effect. However, out of that 8%, about 82 to 83% of that media was correctly counted by the MATLAB code. This led us to create a mathematical model which was able to estimate the actual population of the Lygus media within plus or minus 10% of the real value. We did eventually run some tests with the limited amount of Lygus that we did have. You can see one pictured in the top right corner of this video in the slowed down version. We eventually sent this over to our MATLAB code, not entirely sure how our model would work. After tampering with our filter thresholds, we were finally able to get our model to recognize the Lygus bug in our test. While we are ecstatic about this achievement, we recognize there are still problems that lie ahead, such as mounting this on a tractor and getting it ready for field conditions. While we face these problems in the future, we fully believe that our model will be able to recognize Lygus. Thank you for watching our video, and we hope you enjoyed it.